Well, hello, and thank you everyone for joining us today for our webinar on spatial vector analysis using R. My name is Stefan Gronsdahl. I'm a hydrologist working for Palmer in Vancouver, BC. The webinar today has been organized and put on by the Canadian Society for Hydrological Sciences, which is affiliated with the Canadian Water Resources Association. If you're not already a member, I encourage you all to join. The CSHS puts on all kinds of useful information, such as webinars like this one. They publish useful R packages, and they also put on short courses for water resource scientists and hydrologists. So please go to the website to check it out and sign up. So just a few notes before we begin the presentation. The data used in the examples that we'll see today are available on GitHub. There's a link that should have been circulated in the email that was sent to you about an hour ago. We encourage you all to download the information and follow through the examples after the presentation. We're recording the presentation and it will be posted onto the CWRA website afterwards. And during the webinar today, we will be taking questions. You'll notice there's a box on the right and there's a questions panel. Please use that to type in any questions that you may have. I will be checking them throughout the webinar. I may reply in the discussion window, or I may also interject during the presentation to have Dan answer anything. If we can't get to all of the questions during the webinar, we will post responses to the website or circulate via email after the fact. So now for an introduction. We're very fortunate to have Dr. Dan Moore present this webinar to us today. Dr. Moore is a professor of hydrology at UBC. He's been teaching hydrology for 35 years and has been an active R user for 20 years. Dan is an advocate for the use of R amongst the hydrology and water resources communities. And as we'll find out today, R is also well suited for use with spatial data. So thank you for presenting with us today. Dan, take it away.
Well, thank you for the introduction, Stefan. Hello, everybody. I hope everybody is safe and healthy in these unusual times. Thank you for joining us, and I'm hoping that I can convince you that R is not only good for statistics and data wrangling, but it's also can do a lot of the stuff you normally do in a GIS package. So I'll move to the slide deck. So I have two parts to my presentation. The first is a slide deck that goes through some basic information about the R package that I use. It's called Simple Features, and the data types that are associated with that. We'll have a break at the end of that. I can answer some questions. And then the second part is I'll actually run through some examples to illustrate the applications. Okay, so you should be seeing my slides and the introduction slide. For some reason, it's not advancing. Just hang a sec. Okay, there we go. Okay, now there's a number of packages that have been developed for doing a number of types of spatial analyses in R. For raster data, such as digital elevation models or remote sensing data, there's the raster and Velox packages. GStat's very good for geostatistical modeling. You can access the Saga and GRASS GIS packages from within R using the RSaga and RGRASS packages. And today what I want to focus on is spatial vector data. Now, up until about 3 years ago, the main package that was available for working with spatial vector data was the SP package for spatial. It introduced a number of data types that were called S4 data types, which are very intricate and complicated hierarchical structures. It was very powerful, but it was actually in many ways difficult to use. 3 years ago, the SF package was developed. SF stands for Simple Features, and it's an alternative way of representing spatial data sets. This has made it much easier to work with spatial data sets, particularly in terms of developing integrated workflows. And this is what I'm going to focus on now. So a simple feature is an object in space. It can have a number of attributes, for example, things like area, color, anything else, and it also has a geometry associated with it. The geometry describes where it's located in space and can also describe its shape. I'm going to go talk about simple features and their implementation in R. Now, simple features are data frames, and this is what makes them very powerful and easy to work with. Each row in the data frame is a feature. For example, it could be a watershed polygon, it could be a sampling point, it could be a multi-polygon, for example, polygons representing a number of lakes. The attributes associated with each feature are stored in columns, and the geometries are stored as a list column. And this is a list that has an element that corresponds to each feature. Now, the simplest geometry type is point. Each row represents an individual point as a feature. In addition to this type, there's a number of alternative geometry types, and probably the most common ones that we'd find in hydrology are multi-points, in which case each row in the data frame would have a geometry that has multiple points associated with it. Line strings, which could be, for example, a contour line or a stream segment, multi-line strings, polygons, and so on. In this session, we're mainly going to work with point and polygon geometry features. Just to give you an example of how they're structured and how you can create one, I'm going to work with a simple data set that I use for teaching introductory statistics, which is climate normals for a number of stations near Vancouver. So in this code that you're seeing, read CSV, so the data is stored in a CSV file, and it gets read into a data frame called CN. In case you're not familiar with it, this percent greater than percent is called a pipe. It's an operator that takes the outcome of the preceding function and feeds it in as the first argument of the next function. I like to use it because it's an easy way of creating or performing multiple data analysis steps without creating a lot of intermediate objects. The other thing here I'd like to mention briefly is the use of the here function. There's some links in the associated materials that are on the GitHub site, but this is a very handy way of organizing your work in terms of projects and finding where the data files are. And I've become a big fan of setting up my work this way. Anyway, so this code reads in the CSV file, converts it into a data frame, and then because longitude in this file is a positive number, it makes it negative for west of Greenwich. And the class is a data frame. And so this is just the first 6 rows. There's a station name, elevation, annual precipitation, temperature, snowfall, and then there's a separate column each for latitude and longitude in degrees. Now we create an SF object using the STSSF function. You can convert a number of different data types into simple features objects using this command. And with a data frame, the first argument is the name of the data frame, and then the second argument are the column names that represent the longitude or the X and Y coordinates. And it's important it's in that row, X first, Y second. So long and lat are the coordinates. This then creates this new object, which I'm calling CN_SF, which is a data frame, but it's a data frame that has been augmented to be a simple features object. So just a quick look at it, first top rows. So it's telling us that it's a geometry type, they're all points, so each row includes the information for an individual point. The geometry dimension is X, Y. You could also include, for example, elevation as part of the geometry, so that would be X, Y, Z. The B box or bounding box are the coordinates of the lower left and upper right corner of a rectangle that includes all the features. And CRS is the coordinate reference system. Now in this case, it hasn't been set, so the CRS is NA. Now, when we look at the object itself, it looks the same as the data frame, except that instead of having the 2 separate columns for latitude and longitude, it now has the list column, which has the geometry, and each row has a single point associated with it. And that's the longitude, latitude coordinates. So you need to set the coordinate reference system, and for this we use the stcrs function. You can use either proj 4 string to indicate the reference system, or you can use the European Petroleum Specialty Group, EPSG code, which is a numerical code. So for longitude, latitude coordinates, the EPSG code is 4326. So this then just sets the coordinate reference system for the object. Now, if you want to extract or display the coordinate reference system, say you read in an object and you don't know what the coordinate reference system is, you can easily use the stcrs function to extract that. You can store it in a variable, and you can display both the EPSG code or the proj4 string of the coordinate reference system. So for longitude, latitude, the EPSG code is 4326, and the proj4 string is long lat for projection, and the datum's WGS84, and there's no further parameters. So we have an SF object, and there's a number of operations, basic operations that we can perform with it. One you may want to do is to extract specific attributes or columns. And because these are data frames, we can use the same approaches that you'd use with a data frame. So for example, we could extract it using square brackets and indices. So extract the column number. So in this case here, we're extracting the third column, and we're going to put this into a new object called call_3. Now, it's important to know that when we extract this, the object remains a data frame, and indeed it remains an SF object because it retains the geometry. And so again, if we take a look at this, this object, which has the third column, it has one attribute column, which is the third column, the annual precipitation, and it retains the geometry, and it retains all the other information, point, X, Y, dimensions, and the CRS. We can extract the column using the column name, using the square brackets and the name of the column within the square brackets. Again, this will carry with it the geometry. The outcome remains a data frame, even if you're extracting a single column. If you want to extract the values without the geometry, that is, extract the column just as a vector, then you can use the object name $, column name syntax. In this case, then it extracts the values from the third column, and there'll be an integer vector in this case. You can also use dplyr tools, and I'm a big fan of dplyr for doing my data wrangling. And so in this case, we're taking the simple features object, we're piping it into the dplyr select, and in this case, we're extracting two columns, the annual precipitation and annual temperature. And again, this is a data frame, it's a simple features object. It has the two columns that I've selected, plus it carries with it the geometry. You can extract specific rows in a number of ways. And again, because these are data frames, we can use the same approaches as we would for data frame. So we can use the dplyr filter command in this case. What I'm doing here is I'm extracting all rows for stations that have annual precipitation greater than the median. You can use indices. So in this case, I'm determining the indices of all the rows that have annual precipitation greater than median, and then using the index in the square bracket notation to extract the specific rows. And sometimes you want to just have the geometry. You don't need the attributes. You may just want to be plotting the geometry. And we can extract the geometry using the stGeometry function. This then creates an object which is an FSC. SFC is a simple features list column geometry, and it doesn't have any attributes associated with it. And so this is just looking at the geometry that I've extracted, the first 5 geometries. When you're doing data wrangling with the simple features objects, if you retain the geometry, there's some operations that are very slow if you retain the geometries. So in some cases, you want to remove the geometry during your data wrangling steps. This can be done by using the stSetGeometry function. The first argument is the spatial features object that you want to remove the geometry from, and then you set the geometry to null. This will then create basically just a data frame that doesn't have the list column. And we'll see this as in one of our examples. In some cases, you may want to just extract the coordinates. And in this case, we use the ST coordinates function. The result of the ST coordinates function will be a matrix. The structure of it will depend on the type of geometry. So for example, if you've got polygons, the structure of the matrix will be different than if it's points. For simple point data set like we're working with, the outcome is just a two-column matrix. The first column is the X coordinates, the second column is the Y coordinates. Now, in many cases, you may get data in one coordinate reference system, for example, longitude, latitude, and you may want to project it into another one, like universal transverse Mercator or an Albers. To do this, we use the ST transform function. Now, remember that our object was in longitude, latitude, and we want to, in this example, convert it into UTM zone 10, which is where Vancouver is. So the EPSG code for UTM zone 10 is 26910. We're storing this into a variable UTM CRS, and then we apply that in the ST transform function. Now, when we look at the transformed simple features object, which is CN_UTM, we can now see it's got the same information as before, but it's now projected UTM zone 10N, and the geometry now reflects the coordinates in UTM coordinates. Now, there's two main paradigms for plotting simple features objects. There's the plot command, which is similar to the base graphics plot command, and ggplot. I'm actually a really big fan of base graphics for most of my data plots. I like the clean layout, even compared to the most clean layouts of ggplot. But when it comes to simple features objects, I found that ggplot does a very nice job, and I actually tend to use ggplot. Now, the plot command can be used just very simply, plot and then the name of the object. By default, it will generate a plot for every column that's in your simple features object. So in this case, there's 5 columns, station name, which is categorical, and then 4 numerical variables. And so in this case, it plots a panel for each one, and it color codes it depending on whether it's categorical, one color scheme, or if it's numerical, it uses another color scheme where the colors are assigned according to the numerical values of the variable. If you want to plot just the geometry, you can then use the ST geometry command, as in this example. You can also add some options, just as with base graphics, you can add a lot of options to customize. You can do that, and this is just a simple example where I've added axes equals true, and I've added latitude and longitude graticules by graticule equals true. Now, if you use ggplot, there's a ggplot function geom_sf. Now, normally you might be used to using geom_point, geom_line. There's a special geom_sf that's designed for simple features objects, and the required argument is the name of the simple features object that you want to plot. You don't need to tell it the X and Y coordinates because that's inherent in the geometry of the simple features object. And so this is just a very simple default ggplot map showing the station locations. You can change the projection that the data are being mapped at by using the coord_sf function. So in this case, the CN_sf is in lat long coordinates. Now, by adding this coord_sf and specifying I want the UTM CRS, this will now plot it in UTM. And so when you look at this, you can see coordinates are now UTM coordinates. Now, there's a lot going on in this slide, so I'll walk you through some of the code. So we're going to work with projected data. So we're going to work with the UTM version of our simple features object. I'm also going to modify it. So in this case, I'm going to plot the symbols, and I'm going to scale the color and the size to correspond to the numerical value of the annual precipitation. And in the legend, I want to show the legend as points. I'm going to change the order that the legend shows the variables. So this will show it, so it's, the high values at the top and lower values at the bottom. So I'm reversing the normal order or the default order. These are the labels for the legend. I'm specifying the color gradient to use to plot the symbols scaled by precipitation. And there's two functions here that start with annotation. These are from a package called ggspatial, which provides some tools for augmenting your ggplot maps and for adding things, in this case, a scale bar and a north arrow. So by adding all, using that code, you can see we're starting to look like a real map here. We have a scale bar, north arrow, we have the data points plotted, and they're scaled by color and by size according to the value of annual precipitation. Now, in this example, you can see that even though I'm using the UTM version, the simple features object, by default, ggplot, even though these are plotted in terms of the projected data, the axes are actually still in Latin long. That's the default behavior for ggplot when you're plotting spatial features objects. If you want to plot the UTM coordinates on the axes, you have to add this new layer, coord SF, and the datum equals UTM CRS. This will then have ggplot plot the axes using the UTM coordinates, as you can see in this example here. Okay, so we created a very simple features object. In most cases, you would actually be reading in existing simple features or spatial objects, and you may be wanting to write them to save them. Now, simple features package supports a number of drivers, including Esri shapefiles, KML files, netcdf, GeoJSON, GDB files. There's a whole range of files that it supports. You can view the full list by using the stDrivers function. So to read in a spatial data set, the stRead is the function to use. The main argument in this is DSN, or the data source name. Depending on the driver, the DSN may be a file name. For a shape file, it may be a folder. It may be an open database connection. So it depends on the type of or the format of the spatial data. And the stRead function, based on the type of DSN, will guess what kind of driver it needs to use. So you often don't need to specify the driver, and it will automatically find the geometry type columns. So often you can get away with just the one argument in this, is the DSN. To write out the simple features object for storing it, you can use the stWrite. The main objects are, or the main arguments are object, and this will be an object of class simple features SF or SFC. DSN is the name of the file, folder, database connection to write the data to. The layer, which is the layer to write to. And you can include driver, which says which driver to use, for example, KML or GeoJSON. If you don't include this, stWrite function will guess the driver type based on the digital source name. So for example, if your file you're writing to ends in KML, the function will guess that it's a KML file and use that driver. Now, there's a number of spatial data sets, spatial vector data sets that you can access within R from our packages, which really makes life a lot easier rather than having to go and manually download them. Some of the ones that I've used regularly are R Natural Earth. This provides access to the Natural Earth public domain vector and raster map data. OSM data is OpenStreetMaps. ggmap provides access to base maps from Google Earth, Google Maps, Daemon Maps, and OpenStreetMap. And if you're out here in British Columbia, some data scientists in the provincial government have been kind, and they've developed this nice package called BC Maps, and this provides access to a range of vector data sets relevant to British Columbia. We'll see the application of these in my examples. And so we've talked so far about creating an SF object, a number of the different types of operations you can apply to an SF object. but at the end of the day, we're often wanting to apply GIS operations. And Simple Features package supports a broad range of operations. Some more common ones that would be used in hydrology, and the ones that I use quite regularly are ST crop for cropping, an object to a smaller size, buffering, intersection, distance and area. And you can view the full list by using the methods command class equals SF as the argument. And Stefan gave a plug for the CSHS hydrology page, and Rob Schlompskate asked that I bring this up. So if you want to read more about this project, the CSHS hydrology package, this is the link that you can go to. Okay, so at this point, I'll stop. I finish my slide deck, and we'll see if there's any questions.
Great, thanks, Dan. So we have one question regarding some of the precision that may have been lost on the latitude and longitude.
Right.
There was a comment that it looked like the points may have been falling off a grid. I think it was probably around slide 37 or 38.
No, that's a good observation. And the reason for that is that when I created that data set, I was using a paper copy version of the climate normals, and they had limited precision in which the coordinates were represented. So the fact that the data points fell on a grid just represents the precision of the latitude longitude coordinates that I used as the base data.
Great. One more question.
Yeah.
So it looked like at some point you mentioned you could remove the geometry to conduct analyses a little bit more quickly.
Yep.
Is there an ability, and is it easy to reattach the geometry after the fact using a join function or something like that?
Yeah. Yeah, that shouldn't be difficult. I think you would use, yeah, you could use a join function, exactly, like in dplyr or left join or right join, depending on which order you put the arguments in.
Wonderful. We don't have any more questions regarding this slide deck. So someone asked, is it possible to obtain a copy of the presentation? Yes, the presentation will be available on the website. Oh, I see one more question here. Is there a function to determine if a point is upstream or downstream of a single point?
Ooh, that's a good question. I haven't actually used that. There very likely is a way of doing that. I think what you would have to do is look at the individual points and then test to see whether one is higher elevation than the other, but I've not actually tried to do that sort of operation.
Great, okay. There's no other questions here. So I think we can move into the examples that you have.
Okay, great. And so these examples, you can find them rendered on the GitHub site. So I put the examples together in R Markdown, and so in this case, I've rendered it into an HTML file, and I'm going to walk through 3 examples of increasing complexity. If you want to run these, you'll need to load all these libraries, and Rob has put some instructions on the GitHub site for how to actually load all the libraries if you're not familiar with them. The data should be available. There's one data set that you would have to download or either manually or through the code, and that's the biogeoclimatic ecological zone data set, and that's because it's 120 megabytes, and so we didn't want to put that on the GitHub site because you can download it yourself. But there's directions here about how you need to set up a project on your hard drive to get this all set up if you want to run this yourself. Again, just like to put in a pitch for this here package and the idea of organizing your work within projects. And these 2 links that I provided here provide the rationale and the motivation, and also how you actually do set up your work as projects and use the here function. Okay, so what I'm going to do is I'm going to go back to the R Markdown code, and I'm going to walk through this interactively, and hopefully it all runs smoothly. I ran through it all just before, so it shouldn't be a problem. So rather than having to type in this long proj for string at various places, up front, I'm just going to create it and store it into a variable called CDN_AEA for Canadian Albers Equal Area, just for brevity. Okay, now this first example is I'm going to work with Environment Canada weather station data. There's a station inventory that you can download, and the link for downloading the station inventory is here. Each row in this CSV file is the information for a weather station, and it includes latitude and longitude coordinates, has a number of other metadata for it. So what I'm going to do is I'm going to read in that file using read CSV. There's 3 header lines, so I'm using skip equals 3, so it skips past those header lines. This next bit of code here, and again, this is using dplyr, and this is the pipe function from Magritter. So it reads in the CSV file, it becomes a data frame, it then passes the data frame into the mutate function. Essentially, I'm renaming all the variables. And the reason I'm doing this is that in my own code, I tend to use all lowercase, so I don't have to try and remember whether I've used uppercase or lowercase. Also, some of the variable names in the CSV file have spaces and brackets in them. And so when this gets read in, spaces and brackets each become dots. And so I just find those a little awkward to work with. So again, I'm just renaming all the variables. So I've created new variables with new names, and I'm just selecting those variables that I've just created and leaving out the original columns. There was one odd data point in there that just stuck out. I'm not sure, I think it's an error in the coordinates. So I'm filtering out this point that has an odd longitude. And now what I'm creating is 2 variables, which is the number of years for daily data and the number of years for hourly data for each station. So DLY_Y2, that's the last year of record for daily data. DLY_Y1 is the first year available for daily data, and hourly is last year available for hourly data, first year available for hourly data. So I'm creating these 2 new variables, which are the number of years of record. I then use the STSSF function to convert this data frame into a simple features object using the coordinates lon and lat. Once you create a simple features object, you need to, or it's useful to provide a coordinate reference system. In this case, it's long lat, so I'm using the EPSG code 4326. And then we can just take a quick look at the simple features object to make sure it works well. So we're looking at just the first 10. So I'm subsetting out the first 10 attribute columns just to avoid having, there's over, I think, how many, I can't remember how many there are, but there's a lot. And so you can see each row is a weather station. So the first one's active pass, which is not too far from where I am currently. It has the climate ID, the WMO ID for some elevation, and then it's got the first and last years of records for hourly, daily, and monthly data. And the final column now is the geometry, which is the latitude, longitude, latitude. Now we're going to use a base map layer, just a simple boundary polygon, and I'm going to access this from Natural Earth. And this is a construct that I like to use when I'm accessing data programmatically from the internet. So rather than having to download it off a server every time I run the code, they set up this conditional execution. So it first checks to see if the file exists, the file that I'm going to save it into. If the file exists, then it just loads it. If the file doesn't exist, that means I haven't run this code yet, It then accesses the data from the server, and in this case, I'm saving it as an RDA file onto my hard drive into my project. As again, I find this is just a handy way of avoiding having to access servers all the time, especially if sometimes the server goes down, or particularly if it's a really large data set and you don't want to download hundreds of megabytes every time you run your code. Okay, so just running that. So I now have the, I've loaded in the North American boundaries for the simple features object. I'm creating a simple features object here, STSSF. And again, we'll just look at the first 10 attributes. So the natural Earth data set has, I think it's over 60 attribute columns. And this one that I've got, each row is a country. So the first row is the Bahamas, second is Belize, third is Canada. The geometry column here now is a multi-polygon. For example, Bahamas is a number of islands, and each island would be a polygon. So that's why these are multi-polygon geometries. So this next bit of code, I'm going to extract just the geometry because I don't need all the attribute columns, and I'm going to crop it to an area that just covers Canada. So I'm creating an object called BD_CA. This is a vector, and it's going to be the bounding box. And the bounding box is a vector of 4 values, and they're named. So the names are xmin, ymin, xmax, ymax. And again, it's the coordinates for the lower left and upper right corners. Then I'm going to take the simple features object that I just downloaded for North America. I'm going to extract the geometry, and then I'm going to crop it to the bounding box that I've just defined. And I get a warning message that says, although the coordinates are longitude, latitude, and ST intersection assumes they're planar. That's just letting you know that if you were working with projected data, you might get a different intersection or a different cropping than here. And then I'm going to generate a quick plot. And I like to use the base plot command for quick plots. They render a lot faster than ggplot. So if I'm just plotting something just to check to make sure that everything looks fine, I use the base plot. But when I want to generate a plot, for example, for publication or other purposes, then I tend to use ggplot. And so this is the rendered map. So within my bounding box, and everything looks fine. Okay, so now what I want to do is I want to generate maps showing the stations that have different lengths of record for hourly data. So I'm going to take the simple features object that includes the Environment Canada inventory. I'm going to drop all the rows that have NA values for hourly number of years because I just don't want those in the data set. I'm then going to use the mutate function to create a new variable, which is going to be a categorical variable called hourly class. And I'm going to use the case when function, which is the dplyr function. That's essentially like a nested if else. So that if the number of years of hourly data is less than 11, then the hourly class is going to take on the value 1 to 10 years. If it's then less than 21, 11 to 20, etc. Then once I've created that variable, I'm then going to create or specify that it's going to be an ordered factor. And the reason I want it to be ordered is that this will influence the way that ggplot, or the order in which ggplot renders the different facets. So again, here I'm just taking that hourly class variable, and this will make it an ordered factor. And so this is what the data frame looks like. And so you can see this new variable that I've created, which is the hourly class variable. So now I'm going to generate the map. So I'm using ggplot. The first layer I'm going to put in is the base map. The second layer I'm going to put in is the stations. The color that I'm using is a color that I created, which is a transparent blue, and I like to use that when I'm plotting data that overplot. I'm going to use facet wrap so that each of the hourly classes will go into a different map. And I'm going to specify that I want it plotted in the Canadian hours equal area projection. And so, okay, there we go. So now you can see that what we've got is a series of panels or facets. Each one shows the locations of the weather stations that have, in this case, 1 to 10 years of record for hourly data, 11 to 20 years, 21 to 30, and more than 30 years for hourly data. So this is just an example of creating a simple features object from a data frame, accessing the natural earth data set for use as a base layer, and then doing some wrangling and generating a map, which may or may not be useful for a given purpose. Okay, now, usually you don't just want to map stations. You often want to, for example, you're working on a watershed scale, you may want to find all the weather stations within, say, 100 kilometers of the watershed that you may want to use, for example, in an interpolation scheme. So in this case, we're going to look at the Fraser River Basin here in British Columbia. And I'm going to find all the weather stations that are within 100 kilometers of the station. So the Water Survey of Canada station number for Fraser River is 08MF005. I've already I've downloaded the captured polygon from Water Survey of Canada, and it's on my local hard drive. So this is the name of the file that the object is in. I'm using STRead to read it in, and then I'm going to transform it to BC Albers projection because that's the standard projection for plotting provincial scale data in BC. The BC Albers projection has a EPSG code of 3005. Okay, when you transform and read, often SF will output to tell you what's going on. And so this is just telling us that we now have a simple features object. It's geometry type polygon. The dimensions are X, Y, Z, so it has elevations, not just X, Y coordinates. And it's in Albers projection. Now we want to add a 100-kilometer buffer around that polygon, so we can capture all the weather stations within 100 kilometers. So we use the ST buffer function for that. So the first argument is the name of the simple features object that you want to add a buffer to. The second is the distance, and the distance is in meters. So for 100 kilometers, it's 1E5 distance. Then I'm just going to do a simple base plot just to make sure that everything looks fine. And just in case you're not familiar, this par here, I'm a little bit fussy about my base graphics, and I think that the ticks are too long on base graphs. So this just shortens the tick length and moves the tick labels closer to the axis. That's all that is for. And so this is the quick check plot. So this is the Fraser River watershed, and then that's the 100-kilometer buffer. So everything looks fine. So we've got the Environment Canada inventory as a simple features object, which is longitude, latitude. So again, I want to transform that into BC Albers. In this case, the ST transform, so the first argument is the name of the simple features object you want to transform. Second is the coordinate reference system to transform to. And in this case, I'm using the same CRS as the FR Albers function, rather than writing out CRS separately. And then I'll generate a check plot. Okay, and again, so everything seems to be fine. Everything seems projected correctly. So then we'll continue. So the next step then is you can see that there's lots of stations. We want to subset out just those that are within that buffer. So to do that, we can use the ST filter function. And with EC Albers, this is a point geometry. This is a polygon geometry. So this is essentially a point and polygon search. and they'll be stored in an object called EC_FR, so EC Fraser River. And so then just quick look at the results, everything looks fine. Now I'm going to generate a map, and I'm going to include the British Columbia provincial boundary, and I'm going to include the water courses at a course scale. To do this, I can draw upon data that are available from the BC Maps package. And so the BC bound function extracts the provincial boundary. The water courses _5M extracts the water courses. So then I use ggplot. So the first layer I'm going to add is the BC boundary. The second layer is the buffer. The next layer is the catchment polygon. Then I'm going to add the water courses, and then finally the station locations. And so this is our final map. So again, it's in BC Alberta's projection. We have the provincial boundary. We have the water courses in light blue, the Fraser Basin polygon in red, the buffer in orange, and then the selected data points in blue. Now, the final example I want to work through is working with 2 polygon data sets. And I did this, I chose this one because it actually is working with data sets that are quite large. The biogeoclimatic ecological zone layer in BC is about 120 megabytes. So this just gives you an example of how R works when you're working with realistic large data sets. Now in British Columbia, we have a system called the BEC zone system, biogeoclimatic ecological zones. And this was originally developed for applications in forest management, but it's been found to be a powerful tool for characterizing biophysical site characteristics. For example, Joel Trbilowitz and I and Jim Buttle applied it to predicting stream flow regimes for engaged catchments in BC. Now it's a hierarchical system. The top level are zones, and there's 16 classes. Then within those zones are subzones and variants, and we're just going to work at that upper level of classification. Now, this is a large data set. You can either manually download it from the BC government website, or you can access it through the BC Maps package, which is what I'm doing here. And again, it's a large data file, 120 megabytes. You wouldn't want to download it every time you run your code. So again, I've done this conditional bit of code where if the file already exists on my hard drive, I just load it. Otherwise, the first time that I run the code, it reads in the data through the BC Maps package and then saves it to my local hard drive. Now the catchment boundaries, I'm going to work with 8 of the main tributaries of the Fraser River Basin. So this just creates a vector of all the WSC codes for them. And this function just converts all the lowercase letters to upper, so to upper. Now to read in the Water Survey of Canada polygons, those are available from a Government of Canada website. They're in a GDB format, geodatabase format, which I don't have a lot of experience with. And if anybody out there has experience and you know the more elegant way of doing this, please let me know. But as far as I can tell, you have to read in each polygon individually. So that's why I've had to write a loop that will, I should say I first downloaded all the files onto my local hard drive. They're in a folder called data and WC polygons, and then the data, I download them. And now I'm reading from that downloaded data. Each time through the loop, I'm reading the polygon for a different station. Once I read those into a list, then this next bit of code just reads them into an SF object. Now we want to project these to BC Alberta's projection. So again, I'll use the ST transform, and the coordinate reference system for BC Alberta's is 3005. And what I will use later in this code is I want a data frame that includes just the station names and numbers and their basin areas. For this one, I don't want the geometry, so I'm using ST set geometry null. And then I'm just selecting out station, station name, and basin area. And I'll just generate a map. So everything looks fine. There's 8 polygons there, each representing one of the major tributaries that I've extracted. Now, the analysis that I want to perform is I want to calculate what the fractional coverage of alpine zone or alpine vegetation is in each one of these catchments. So to do this, I'm noticing that in the Beck zone system, there's 3 different classes that represent alpine cover: the coast mountain heather alpine, interior mountain heather alpine, and boreal altai fescue alpine. So my first operation is to apply a filter to filter out all the features, all the polygons in the Beck zone coverage that are one of those 3 types. So this is just standard dplyr filter function. And so everything looks fine. So now I'm going to generate a map that shows the BC border and the catchment boundaries, and with the alpine polygons. Sometimes ggplot takes a little while to render, so we'll just trim in it here. This is taking quite a while. Oh, there's finally. Good. Okay, so this just shows the map now. It's the BC boundaries, water courses. The gray are all the polygons that have alpine vegetation, and the red lines are the catchment polygons. And so what I want to do is to do an intersection to find out what fraction of each of these watershed polygons is alpine. So just as a check, or sorry, this next step here is going to do the intersection. So I use the ST intersection function. The first argument is the catchment polygons. The second argument is the polygons for alpine vegetation. This will take a bit of time to do the processing. Okay, so this is the output. And so what this intersection does is it goes through all the polygons and it finds all the, or it goes to the catchment polygons and it finds all the alpine polygons that intersect with the catchment polygons. So the first set of features or first set of columns are the catchment names. This next set are all the features associated with one of the Beck zone polygons. So for each of the catchment polygons, the number of rows, each row corresponds to a different polygon from the alpine data set. That's the ST intersection. The geometry here now is the geometry of the intersected polygon. So just as a check, we're going to look at the Nahatlatch River. It's one of the catchments. So I'm going to filter out the Nahatlatch catchment from the catchment polygon using dplyr filter. And then we're going to generate a map just showing the watershed polygon for Nahatlatch and then the intersected alpine polygons. So this is the black line is the catchment polygon for Nahatlatch River. The light blue is the alpine area, and the white represents the valley bottom. So everything looks fine. So the next code chunk then first calculates the areas of each intersected polygon. It then adds those areas to my simple features object as another attribute column. Then the next step is, and again, this is one of those cases where you want to remove the geometry to make it run faster, is I'm going to go through the simple features object, and then for each station, I'm grouping by station, I'm going to sum the polygon areas for the alpine polygons. And this will give me the, in the end, the total area within each catchment that's alpine. So each station, and then this is total area of alpine coverage within each polygon. Now remember, we had 8 catchments originally, and there's only 6 listed here. That's because 2 of the catchments don't have any alpine cover, and so they don't get captured by this data wrangling step. Then the final step is to compute the fractional coverage. So I'm reading in the station list that I created earlier, WSE_stations. I'm doing a join with the alpine areas, which I just created. We're joining it by station. And then I'm doing a couple of calculations. So I'm calculating a variable called WC_alpine. And this is because when I do this join, the catchments that don't have alpine will have NA values for the alpine. So I'm just replacing those NA values with zeros. Then once I've done that, then I'll calculate the alpine percent by calculating the alpine area divided by the total basin area and multiplying by 100. And so now I've reached the end, which is I now have a list for each of my catchment polygons. I've calculated the alpine cover as a percent. And that was the last of my examples. What I've really wanted to do is not to provide a comprehensive coverage of using SF and dplyr, but just to give you a taste of the types of things that you can do. And as I mentioned, this is this last example was based on a data set that's quite realistic, very large data set, and you can see it performed reasonably well. And at that, I'll go back to Cameron and see if there's any questions.
Great, thanks, Dan. Just one thing to remind the audience, the code that Dan has been running is available from GitHub. You can download it and use it outside of GitHub if you want. The link to it was circulated in the email that was sent out about an hour before the webinar. So you can go and access all these examples there. Okay, so we've got a few questions. If people have more questions, please use the questions window on the right, and we'll continue answering them. So Dan, one of the questions, or I guess this is a comment, this first one, we might be able to download the BEC zones and other BC data using the BC data package. Now I know we're using the BC maps data package. Is this the same thing, or are they different packages?
Oh, okay. There's 2 packages. One is BC Maps, and that's available through CRAN, the Comprehensive R Archive Network. You also need to download the BC Maps data package, which actually has the underlying data, and that is you can access that from GitHub. And okay. in the documentation, there's instructions for how to actually install the BC Maps data package.
Sounds good. Another question that has come up is, I think it might be worthwhile, perhaps not everyone is familiar with R Markdown, and there's some interest in the code that you've shared with R Markdown. Would you mind just elaborating briefly on its functionality?
R Markdown, be happy to. R Markdown is a really handy application. It runs really nicely. You don't have to run it within RStudio, but it works really nicely within RStudio. It's a Markdown, so it's based on Markdown. So Markdown is a simplified markup language. So HTML is a markup language, which is text with tags inserted into it that control the formatting. Markdown is a markup language that's been very simplified, and the idea is to try and reduce the complexity of the tags so that you can actually look at a Markdown file and you can get a good sense of how it's going to look when it's rendered. R Markdown is a version of Markdown that allows you to insert code chunks. And before I get into that, I'm just going to say that one part of the R Markdown file is what's called the YAML header, YAML. And I think YAML stands for yet another markup language. I'm not sure, but this is called a YAML header. It starts with 3 dashes at the top, ends with 3 dashes at the bottom, and you control a lot of the high-level formatting by what you put into the header. For example, for output, this is an HTML document, but you could put PDF document. You can create Word documents from this. You can include references, and if you've got references, you can include a bibliography file where it can look for the citations, which are in BibTeX format. Yeah, so this is the header that provides a lot of information, controls the titling. A first order heading is given a single hash mark. So when this is rendered, or it's called knitted into the final document, this will become a first order heading. That's a first order heading. 2 hash marks will make a second order heading, 3 a third order heading, and so on. You can include code chunks, and a code chunk has 3 backticks, curly braces, and an R. And the reason you have the R there is that you can actually include different languages. I believe you can include Python code in here as well. And then for this code chunk, there's some options, which says don't print out the warnings and don't print out messages as it executes this. The code chunk ends with 3 backticks. And when you knit the R Markdown file, the first step is that R Markdown goes through and it runs all the code chunks and it executes all the R code, and then takes the output from that R code and inserts it into a new Markdown file. Then that Markdown file is then rendered. And so the nice thing about this is that you can actually have dynamic code in here, and every time you render it, it will rerun the code, which means you can have dynamic documents. For example, if you change your input data, you can rerun the document and it'll update everything, including the figures, any tables that are associated with the data. And I actually am doing almost all my manuscript writing in our Markdown now. And then I end up working with creating a LaTeX file from it.
Thanks, Dan.
Yeah.
One of the, I guess, follow-up questions to that is there anything in particular that you need to use R Markdown? Like, do you need to download packages or anything else that's external to our studio?
R Markdown, and I think if it's been so long since I've done it, I can't remember. I'm sorry, but I think if you install our studio, I think you have R Markdown available, but I'm not absolutely certain. It's been too long since I've done that. I should say that R Studio has a lot of really good tutorials on working with R Studio and R Markdown, and I'd point people in that direction.
So another question, thanks, Dan. Another question that has come up is if there are similar examples of the kinds of data that you used in this analysis from other provinces. Manitoba and Alberta have been given as examples. Are you aware of whether these data are available elsewhere?
No, I'm sorry, I'm not. I know, for example, in Ontario, there are some very good JS layers for land cover. I'm not familiar with Alberta, Saskatchewan, or Manitoba, though. But I mean, I'd be surprised if there weren't some provincial level databases with land cover or similar types of coverages.
Okay, another question. Is it possible to merge 2 stations as well as their data using a buffer distance in the SF package?
I'm not quite sure to merge 2 points. I'll take a guess. There, when you run the intersection, you can specify the geometries as being exactly matching or within a distance. So you can actually, when you're trying to match up 2 data points to see if they're the same, you can have a tolerance in there. I've not done that myself, but you can specify exactly equals or close to, essentially.
Great. Okay, another question here. I'll read it all. This was great. Thank you. If you're interested in giving another webinar for us, this person would love to see a walkthrough of your code on channel network delineation and intensity, duration, frequency. Yeah, they say they'll check out your code on your website, but they appreciate the R Markdown files that you shared today. I guess
Yeah, the goal is actually to do a series of these ones. I will, in the future, we plan to do one on raster data processing, and then a follow-up one on digital train analysis that would include the catchment delineation. I'm not going to be able to do that until after the next teaching term because I'm teaching 2 courses online for the first time, and my colleagues tell me that you basically double or triple the amount of time it takes to prepare for online delivery. So I'm making sure I'm not committing myself to anything extra until at least the next term's over.
sounds good. The take home there is that there are future webinars in the works, so stay tuned.
Yeah.
That's great. Thanks, Dan. There's no other questions. One is, are R and Python similar programming languages?
R and Python are similar in that they're both open source. They're both very popular within the scientific community. I would say that they have different niches. Python is particularly good if you're more coming at from a software engineering point of view, or you're trying to write applications and you're doing server level operations. R is particularly good when you're dealing with statistical analyses, statistical modeling, because the R language is built from the ground up to be an engine for data analysis and statistics. In fact, I was just noticing that at the American Geophysical Union fall meeting, which is just started, there was a session on how to use R and Python together. And the motivation for it is the fact that a lot of hydrologists and other scientists use R, whereas a lot of the geophysical community uses Python. And so there's these tools that have been developed, some in R, some in Python. And so there's sort of a digital divide between these two communities that have these great tools. And so the workshop was on how you can actually work with both R and Python. And as I mentioned, I believe that you can run Python code within R Markdown. So, and I know that there have been discussions between the developers of R and Python to talk about ways of developing synergies between the two programming languages.
Great. Okay, one more question has come in here. Can you comment on the speed of R for complex spatial operations relative to systems like QGIS or ArcGIS, or code-based packages like .spatial or the net topology suite?
No, I can't really speak to that because I don't have a lot of experience with those other packages. But just as an example, the third example that I provided today was working with one of the data sets was 120 megabytes. And so you could see that, it took a little bit of time to work through, but it certainly wasn't unmanageable. If speed is an issue, you can use GRASS or Saga from within R, and in particular, for raster data processing, I tend to use Saga from within R, because Saga is very fast.
Okay, just a comment from an attendee. There are ecological information polygons at North American scale to eco districts. Many provinces have their own data and systems, but the North American set has a common basis.
Yep.
And then another question, when would you use R versus ArcGIS, or I guess QGIS, or whatever your GIS system is? Can R do all of the ArcGIS functions?
I'm not really the best person to ask about that. My GIS needs are not that extensive. Mostly, in fact, a lot of what I do is really just digital terrain analysis, watershed delineation, and then simple intersections like I just showed today. So I can't really comment on the broad range, but if you look at the methods that are available in the SF package, that'll give you a sense of what is possible. And my understanding is that you can do pretty much any vector operation within R.
Great. There's another comment about the BC Maps package. So the BC Maps is a more general data package for layers that aren't. Sorry, I'm just reading this. This is a more general data package for any layers that aren't included within BC Maps. So I think they're referencing the BC data package. There's
Right.
only a subset of BC Maps data within the BC Maps data package.
Right.
The newest version of BC Maps doesn't require you to download data outside of the package. So,
Oh, okay, good. That's good. That's good to know.
great. Okay. I think that's it for questions. So thanks again for everyone for attending. I hope you learned something, and yeah, stay tuned for future webinars.
Okay, goodbye, everybody. And as our Dr. Bonnie Henry says, be kind, be calm, be safe. Take care.